Welcome to the 23rd lecture on computational mathematics with SageMath. In this lecture, we will look at some applications of integrals. In the last lecture, we looked at application of integral as a area. Basically, integral is defined as a area, signed area under the curve. So, we look at applications like finding area under a curve or between two curves, finding volume, surface area and things like that. Okay. So, let us look at for example, if you have to find area under a curve between two curves, so we can use this integral. So, first let us take an example. Suppose you have a curve f(x) which is sin x minus x into e to the power minus x square, and you want to find area under this curve between x equal to half and x equal to 3. So, this is simply the integral of this function between half and 3, that is all. So, and you can actually define plot this shaded area using this plot function. Inside this plot function itself there is something called fill. Fill 0 will give you filling between the graph of the function and the x axis, and you can define what is the color of that fill, and you can also define the opacity of that fill. So, that is what is demonstrated in this Sage code. You are defining the function, then you define the area as a integral of f(x) from x a to b and take the numerical value, and then plot the graph of the function, plot the graph of the two lines x equal to a and x equal to b in dotted style, and then print the actual area, right. So, that is what you can see here. That is the area under this curve plotted as a shading, and then the actual area in this case, the area under this curve is 1.3461 and so on, right. Similarly, if you have to find area between two curves, say for example, we want to define area under the curve between the curve f(x) equal to sin x minus x into e to the power x minus x square and gx equal to cos x minus x into e to the power minus x square, again between 1 and 3.5. Then again you can do the same thing. So, if you try to plot graph of these two functions, it may happen that one function lies above the other function. So, in that case you can simply take the difference of the two functions and find the area. And in this case, if you look at this, is the above one is the f of x, below one is the graph of g of x, and f(x) is always above g of x between this limit. So, in that case area of this curve you can simply find by taking the difference between the two values f(x) minus gx and calculate its integral. So, that's what. So, this is straightforward, but however it can happen instead of, for example, let us say if I want to find out between, let us say again 1 and let us say 6.5. Now, in this case you see here, now at this point one has to first of all find out what is the point of intersection. To the left of this, the f(x) is bigger than gx, whereas to the right of this gx is less than f of x. So, in that case you need to find out this point of intersection of these two functions, and then calculate the area to the left of which and area to the right of which. One first one will be to the left of this point will be f(x) minus gx the integral, and the right hand side will be gx minus f(x) integral. Okay. So, this is not the correct answer actually. So, one has to split this integral and then find out. This is not correct one. Okay. So, you can find out for example, let us see how do I find out intersection of these two curves. So, you can say find underscore root of f(x) minus gx. So, I will say f(x) minus g of x between, let us say 1 and 5 to begin with. So this is 3.92699. So that's the this. So if I store this in a value C1, then the actual integral is going to be integral of so let me write this. This will be the left hand integral. So this integral a to C1, and then next one will be integral of gx minus fx from C1 to b. So if you add these two, take its numerical value dot n, and here also dot n, that's the actual integral, right. So this is how you can find a area between two curves, two intersecting curves, right. Let us take this example. So this is again similar to this. So find the area enclosed between two curves. So if you try to plot graph of these two functions together, then the enclosed area is only between this and this, right, between this intersection point and this intersection point. So that you need to first find out. So let us find out the solution of this fx equal to gx. Solution dictionary equal to true. So it says that it intersects, the two curves intersects at square root 10 and minus square root 10. So let us store these two value in a and b. So these are the a and b, which is minus square root 10 is a or square root 10 is b, and we want to find area between these two curves. So here in this case you can see here the blue one, which is the graph of fx, is above graph of gx in this region. Therefore in order to find the integral, all we need to do is first this is to plot the shading of the area between these two curves, and then to find the integral, that is area, you simply need to say fx minus gx, integral of that from a to b, and that integral is 80 upon 3 square root 10, right. So if you want you can find dot n, and this will give you the numerical value. Another application of integral is in finding the arc length of an arc. Now suppose you have an arc or curve which is defined by y is equal to f of x function, explicitly defined function between a and b. In that case the length, arc length, is given by integral of 1 up square root 1 plus dy dx whole square from a to b. This dy dx 1 plus dy dx the whole square, this is what is called length, the ds, generally we denote this by ds, that is, and so you are integrating ds from a to b, that is a small arc length, a small change in the arc length, that is the ds, and then you are integrating from a to b. Similarly, if you have a curve defined by parameter, say x equal to xt, y is equal to yt, and then in this case the arc length will be square root x dash t square plus y dash, this would be y dash t square, second one should be y dash t square, and then integrate from a to b, right. So let us take a simple example. So suppose you have a curve y equal to log x minus x square upon 8 between 1 and 2, then its arc length, first let us plot graph of this function. This is how the graph looks like, and its arc length is integral of square root 1 plus derivative of f with respect to x square, and x varying from 1 to 2, this is log 2 plus 3 by 8. Similarly, if you have a curve which is defined by x is equal to cos t and y is equal to sin qt, so here x is equal to curve x is equal to cos qt, y is equal to sin qt. So if you look at this x and y, they satisfy a relation. If you look at x to the power 2 by 3 plus y to the power 2 by 3, this you will get cos square t plus sin square t, which is 1. So that's the relation, implicit relation. And if you try to plot graph of this function using parametric plot, this is how it looks like. This is a very famous curve. I think it is known as asteroid. So you want to find arc length of this this curve. So, this curve you can just see that it is actually symmetric. So, whatever is the length in the first quadrant, the total length will be 4 times that. So, we can try to find out arc length in first quadrant and then multiply that by 4. Okay. So, this is the ds square, which is f1 t the whole square plus g1 t whole square, and f1 and g1 are derivative of f and g. Here we have taken x coordinate as ft, y coordinate as gt, right. So, that is the area element. Now, this take the numerical integral of this from 0 to pi by 2, because in first quadrant the t varies between 0 to pi by 2, and multiply this by 4, you will get the area. This is actually 5.9999. So, this is 6. The total length, arc length for this curve is 6. Okay. Similarly, if you want to find surface area of surface of revolution, we have already seen how to plot surface of revolution of any curve, and then the surface area of surface of revolution of a curve y equal to f x between x equal to a and b about x axis is given by this formula. This is a integral from a to b 2 pi y into this area element ds, which is 1 plus dy dx the whole square, and in case you rotate this about y axis, then this formula is integral from c to d, that is the domain in which x in which y varies. So, here it should be x is equal to gy, actually x is equal to gy. So, this is integral from c to d 2 pi x into integral square root of 1 plus dx by dy the whole square. So, using this let us try to find for example surface area of the sphere x square plus y square plus g square is equal to r square. Now, this sphere you can actually obtain by surface of a revolution by revolving, let us say, upper semicircle from minus r to r about x axis. So, if I define a function f x is equal to square root of r square minus x square and try to plot the graph, this is the graph of the semicircle, and then if you revolve this, draw the revolution plot 3D of this curve between minus r and about x axis, you will get a sphere. So, that is the sphere, and that is this is the curve which is rotated like this about x axis. So, if you try to find the surface area of this, so f x is square root of r square minus x square, and then its integral, that is the surface area, this is by formula 2 pi into f of x, that y is f of x into square root of 1 plus dy by dx whole square, that is same as saying f dash x the whole square between minus r to r. You should get this as 4 pi r square. That is the surface area of sphere. Similarly, if you want to find, let us say, surface area of surface of revolution about this curve f x equal to 1 x plus cos x between x equal to 0 and x equal to pi about x axis, then again you can do that. So, let us plot graph of this surface first. So, that is how this is the curve, and if you try to plot this surface, this is how it looks like. This is quite nice. This is the surface, and whose surface area will be given by integral from a to b. A and b here are mentioned already, 2 into pi f x into square root of 1 plus f dash x the whole square from a to b, and this integral, that is the surface area, turns out to be this value. So, you may need to compute what is its numerical value, because it is just giving you the output as the integral which we have entered, right. So, if you are unable to find the integral in closed form, in numerical form, then you may use dot n or use numerical integral for arc length and surface area, etc. Right. Similarly, let us look at how to find the volume of a solid, or when we obtain this solid by revolving some region which is let us say bounded by y equal to f of x between a and b about x axis, then this is given by formula v is equal to integral of a to b ax dx, where ax is the cross sectional area, and which is the cross section area in this case will be the pi and the height at x, which is f of x the whole square. Similarly, if you rotate about y axis, the x equal to gy curve, this cross section area, if it is ay, this will be pi into gy the whole square, integrated from c to d. Whereas if you have two if you have region bounded by two curves, y equal to f of x and y equal to g of x, and let us assume that f x is greater than equal to g x, in that case you can take the difference of the outer surface minus the inner surface and then find the volume, right. So, these are the formula. I am sure all of you must have done this these things in your regular classes. So, let us take some examples. So, for example, again if you look at what will be the volume of the sphere. So, again we can obtain a sphere by revolving the semi circle about x axis, and if you use the formula v is equal to integral pi into f x the whole square, x varying from minus r to r, this is pi by 3 4 by 3 into pi r cube, that is the volume of sphere of radius r. Let us take next example as computing volume of an ellipsoid. So, one can obtain ellipsoid by the surface of revolution of rotating or revolving this ellipse x square upon a square plus y square upon b square equal to 1 about x axis. In fact, you can just take upper part of this ellipse and rotate about x axis between minus x equal to minus a to x equal to a, you will get an ellipsoid. So, let us try to first plot graph of an ellipse between minus a and a. So, this is x square using implicit underscore plot x square upon a square plus y square upon b square is equal to 1, x varying between a minus 0.5 to a plus 0.5. Here we have taken a as 1, b as 2 and b varying between b minus 0.5 to b plus 0.5. So, this is the ellipse. Now, if you take upper portion, upper half ellipse, that can be obtained as y square upon b square is equal to 1 minus x square upon a square. Therefore, y square will be 1 minus x square upon a square the whole thing into b square, and then y will be square root of that. So, if you take that function f x is equal to b into square root of 1 minus x square upon a square and revolve this or rotate this about x axis between minus a, and then you will get an ellipsoid. So, that is what you have. Let me make it slightly smaller. So, this is the ellipsoid. You can rotate this and see that is the upper semi ellipse which we have rotated, right. And you can compute its volume by the formula integral of pi into f x the whole square, x varying between minus a, and here f x is b square into 1 minus x square by a square, the square root. So, this volume is 3 by 2 into pi into a b square, that is the. So, you can see here in these are the symbolic integrals which Sage is able to find, but so it is not just that it will find the numerical integral, but it can also find the symbolic integral in majority of the cases wherever the integral is possible in closed form, right. Next example, let us look at suppose we want to find volume of the solid obtained by the region y equal to x and y equal to square root x about the line x equal to 1. So, let us first plot this the region or the two curves. So, red one is y equal to square root x and this blue one is y equal to x curve, and this is the green vertical line is x equal to 1. So, you want to rotate this portion, this region about this green line, that is the axis of revolution in this case. So, again you can obtain that surface by surface of revolution, and in this case you have two curves, one is outer curve, another one is inner curve. So, let us plot S1 as the revolution of f, which is y equal to x, and the second one S2 as a revolution of gx from 0 to 1, and here you are mentioning the axis of rotation as 1 0. So, it is passing through 1 comma 0, and then you are rotating about z axis, and then if you put all these things together, you will get the surface. This is the solid surface. So, you can though here it is plotted and it may sound it may look hollow inside, but the hollow inside is the solid you can think of, because here we have taken the region inside this as a hollow one, right. So, you can find now the volume of this surface of revolution. So, in this case, if you look at the cross sectional area, which will be parallel to x axis or perpendicular to y axis, this you have to calculate from x equal to 1. So, it is going to be the outer one is going to be 1 minus y square, the whole square of this, minus the inner cross sectional area, which is 1 minus y the whole square. So, and therefore, this integral is going to be pi into ay the whole ay integral varying from 0 to 1. So, that is pi by 5. That is the volume of this solid obtained by revolving the area between these two curves about x equal to 1. You could have rotated about x equal to 2, or you can rotate about x axis about, let us say, y equal to 1. All such things you can do it quite efficiently and very easily, right. Let us look at another problem. This is a surface obtained by revolving this curve y equal to 1 by x about x axis from 1 to infinity. This is what is called Gabriel horn surface. So, if you try to plot graph of this function, this is how it looks like between 1 and 10, and if you take instead of 1 and 10, if you take 1 and 50, then this is how it will look like. Now, this you want to rotate about x axis. So, when you rotate about x axis, let us say, then this surface will look like this. Okay, this is become, so let me, instead of 50, let me make it 10, because 50 will be too big. So, and then rotate about x axis, then this surface looks like this. Yeah, this is how it looks like. Let me rotate. So, you can see here, this is the beginning, and then it is kind of becoming very thin and thin. This is what is called Gabriel horn. Now, interesting thing about this surface is that if you try to find the surface area of this surface of revolution, for example, if I say surface area calculated between 1 and 20 using the formula for surface area, this is 1254. If I go up to, let us say, instead of 50, if I go up to instead of 20, if I go up to 50, this has become 8752. If I go up to 500, then this is, and if I go up to 5000, it is, you can see here, this is becoming very large. So, the surface area is increasing, whereas what happens to the volume? If I look at the volume of this Gabriel horn, so we have to calculate the integral of this fx square into pi from 1 to infinity, right. So, this is actually pi. So, the volume is finite, whereas surface area is infinite. So, that is the interesting thing about this Gabriel horn surface. Okay. So, let me leave you with some exercises. The first one is graph the surface y is equal to 1 plus x square to the power 3 by 2 between 0 and 4 and find its arc length. The second problem is again to find arc length of this function defined implicitly y square is equal to 1 plus 2x the whole square between x between 0 and 1, y positive. Third one is find the arc length of the curve defined by parametric curve x is equal to e to the power sin t, y is equal to e to the power cos t, t varying between 0 and pi. The third one is find the volume of the solid of a revolution of y equal to cos x between 0 to pi revolving about y axis. And the fourth one is again you look at a region R which is bounded by two curves y equal to x square and y equal to x minus 3x cube. Calculate the area of R and then calculate the volume obtained by rotating r about x axis, and similarly let us say this is I think repetition, and the volume obtained by rotating r about y axis. So, these are the few practice problems. I will see you in the next lecture where we will look at maybe one or two more applications, then we will move on to multivariable calculus. Thank you very much.